Welcome children, welcome. In this class, we are discussing some typical questions from the chapter 3, that is classification of elements and periodic properties. Once again, welcome all to the discussion. Yes, we have the first question as you see here. Regarding the electronic configuration of gadolinium, atomic number 64. A question which appeared many times, more than once for the competitive examinations, asking for the electronic configuration of element GD, which is coming somewhere in the mid of F block, right? So that itself is able to understand what the configuration is. It will be having F7 configuration, and the answer must be first choice F7 configuration, and the configuration for GD is 4F7 5D1 6S2. That is the electronic configuration of gadolinium. And it is easy to identify. It is coming somewhere in the mid area where the electronic configuration of F orbital filling happens, and is coming to somewhat half. Okay, that is the thing. And you know the electronic configuration of F block elements, N-2, F1 to 14, N-1, D0 to 1, NS2. Right? Next question. The formation of oxide ion. You see, oxygen accept an electron giving O minus, and the value is 141. And O minus accepting one more electron, you get a value, O2 minus, the value is endothermic. That is the point. So electron gain enthalpy, first value, not only for oxygen, for almost all elements. Electron gain enthalpy, first value negative, second value positive for all elements. You know, first value coming positive for noble gases, nitrogen, etc. The first electron gain enthalpy value itself is positive. Meanwhile, almost all elements in the periodic table, the first electron gain enthalpy is negative, high negative given by halogens. And oxygen, the first electron gain enthalpy is minus 141. And the second electron gain enthalpy, and that is for all elements, it is okay, like that only, highly positive. What is the reason? What is the reason? The most suited answer is, see, this is the question there in the NCERT. This is the question there in the NCERT exemplar, and a previous question also. Option 3 is the correct answer. In the karyam, electron repulsion outweighs the stability gained by achieving noble gas configuration. Of course, it is getting noble gas configuration, but there is interelectronic repulsion. Already there was 8 electron in the 2p orbital, right? One more electron came, and one more electron comes. There is interelectronic repulsion, which causes the endothermic nature of that system. Option 3 is the correct answer. Okay, next one. So not only for oxygen, for almost all elements, neutral atoms, the second electron gain enthalpy will be essentially positive. Okay, next. Third question. Element 114 will be 14th group, 115 will be 15th group, 117 will be 17th group, 118 will be 18th group, 114 will be 14th group carbon family, 14th group carbon family, second choice. And the element, all of you know, it is flerovium. It is flerovium, the newly named element. You can find in the NCERT textbook almost all elements in that row, including up to noble gases 118 organozone is named in the new NCERT textbook. All of you see that. Next. Most acidic. This is basic. This is basic. This is basic. And this is amphoteric. Amphoteric means acidic as well as basic character. The rest all distinctly basic, while that one is amphoteric. Beryllium oxide is well known. Amphoteric oxide showing acidic as well as basic character. So that is the answer, while the others are distinctly basic in nature. Okay, next. Second choice. The second period elements, correct increasing order of first ionization enthalpy. For the elements lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, you know. Refer the textbook. A graphical representation given going like a step by step, 2-step, 2 points, there are exemptions. I think you remember it is between beryllium, boron and between oxygen, nitrogen. Oxygen less than, see, generally ionization enthalpy increases across the period. But there are 2 exemptions between beryllium, boron and nitrogen, oxygen. Oxygen less than nitrogen or nitrogen greater than oxygen, and beryllium greater than boron. So what is the answer? There is an exemption between boron, beryllium, boron less than beryllium, and there is an exemption between oxygen, nitrogen. First choice is the correct answer. First choice is the correct answer. You can find a difference between these two and these two. You know why nitrogen is greater? All of you know half-filled electronic configuration of nitrogen. Nitrogen maintain half-filled electronic configuration, and half-filled and completely filled configurations are extra stable. Nitrogen having P3 configuration. That takes nitrogen to be a slightly greater value. While between boron, beryllium, beryllium is having 2s2 system and boron having 2s2 2p1 system. So here electron is removed from p orbital and here electron is removed from s orbital, which is paired. So removal of electron from s orbital, number one, paired electron makes bit tough. That's why beryllium slightly greater than boron. While nitrogen, oxygen, nitrogen having P3 configuration. Padichittonda, right? Next one. Ionization enthalpy of sodium given 495 kilojoule per mole. How much energy in joule must be required to convert all atoms of sodium to sodium ion present in 2.3 milligram sodium, right? So ionization enthalpy of sodium given, IE value given as 495 kilojoule per mole. That means 1 mole sodium. For ionization, the value required is 495 kilojoule. 1 mole sodium means 23 gram. 23 gram, you need 495 kilojoule. Therefore, 23 milligram, how much will be required? By 1000, that is 495 joule. Kilojoule by 1000 is joules. So it is 23 gram require 495. 23 milligram require 495 joule. And hence our answer, 2.3 milligram, you need 49.5 joule. That's it. Which one? Option B. Option B. So for 1 mole ionization, you need 495 kilojoule. 23 gram, that is the molar mass of sodium, 23 gram per mole. So for 23 gram, you need 495 kilojoule. 23 milligram, 495 joule. 2.3 milligram, 49.5 joule, right? Next. Option B. Outstanding property of element with the valence electronic configuration S2P6. They are noble gases. S2P6 is noble gases, chemically inert. They are chemically inert, right? Next. A sudden large jump between the values of second and third ionization energies would be in second and third, large jump. Option D. After removal of these two electrons, the third electron lie in the noble gas core. After removal of the two electrons, the third electron lie in the noble gas core. And it is tough to remove. So there will be a large jump between second and third. You see, you are removing this last electron. Okay, low value. You are removing again electron, low value. Now the third electron will be removed from here, which you require a very high value because the electron is available in the inner core. Okay, so that's why there is a large jump between second and third. Okay, next. Ninth question. Decreasing acidic nature. Decreasing acidic nature. Acidic nature, all of you know, depends on the electronegative nature of the element, right? Higher the electronegative element, greater the acidic nature of its oxide. So acidic nature of oxide depends on the electronegative character. So greater the electronegative nature of the element, greater will be the acidic nature of the oxide. So which one is the most electronegative in the line up? Is nitrogen. So that is most acidic. Then carbon, then boron, then beryllium oxide, you know, amphoteric, and lithium, it is basic in nature. So this is basic, amphoteric, acidic, acidic, acidic. This is most acidic. Next. Element XYZ having atomic number A plus 1, A plus 2 respectively. This is X, Y, Z. So X is A, Y is A plus 1, Z is A plus 2. Z is an alkali metal. So this is an alkali metal. Quite obviously you can understand. Z is alkali metal, that is A plus 2 alkali metal. So Y is A plus 1, previous group. Alkali metal, previous group eda? Noble gases, right? You go back. So alkali metal, the previous group is noble gases. The previous group is X. Adeda halogens. So what is the answer? So if this is group 1, this is group 18, and this is group 17, 17, 18, and the next one is 1, like that. So it is option D, 17 and 18. X is noble gases and Y is, X is halogens and Y is noble gases, and Z is the next continuation, alkali metal. Next. Electron affinity of halogens. Electron affinity of halogens. Electron affinity of halogens depends on the electron gain enthalpy, negative electron gain enthalpy. This is the order of negative electron gain enthalpy. You have studied. This is the order of negative electron gain enthalpy, and same is the order of electron affinity. The high negative electron gain enthalpy, chlorine, and fluorine comes only second position. You have learnt because of small size and interelectronic repulsion. Due to small size and interelectronic repulsion, see, all are having 7 valence electrons, and the 7 valence electrons available in 2p orbital in case of fluorine and 3p orbital in case of chlorine. So fluorine, the orbital is small and there are 7 valence electrons, which creates maybe it's creating an interelectronic repulsion, and when you try to add electron, there is more repulsion. And even though the expected electron affinity greater for fluorine, it is coming only after chlorine. Chlorine is maximum. Chlorine maximum, then fluorine, then bromine, then iodine. So what will be the nature of the graph? It must be this graph, right? It must be this graph. This is the one suitable graph. You have fluorine, chlorine, bromine, iodine. So fluorine, chlorine, bromine, iodine. That must be the order. Chlorine maximum, then fluorine, then bromine, then iodine. Option C is the suitable graph. Right? Next. Which ionization involve greatest amount of energy? Greatest amount of energy. See, this is low value. This is low value. Sodium removing electron, alkali metal. And this can be large. This can be large. You are removing second electron from potassium. See, potassium having 1 valence electron, removing electron from that. Okay, low value. Then what about removing the second electron? Second electron you are removing from the inner core. That will be a large value. And there is definite possibility you mark this as answer, but the correct answer is option C. See, of course, here it can be a large value, but here it will be extremely large because it is carbon. Carbon, first ionization enthalpy itself is large. And here we are talking about removal of the third electron. You have removed first electron, you get C plus, just assume. You have removed first electron, you get C plus. That itself is a large value. And then you are removing the second electron. That will be pretty large. And now you are removing the third electron. That will be again large. You have learned the subsequent ionization enthalpies keep on increasing. So first value of carbon itself is very large. Second value again large. Third value, it will be again large. So it is never comparable with this. Of course, this can be large, but never large enough to be like this. The answer is option C. Right? Next. Option C. Correct order of polarizing power. Correct order of polarizing power. You have learned about the polarizing power. Polarizing power depends on the size of the ion, charge of the ion. So higher the positive charge, smaller the size, higher the polarizing power. A detailed discussion coming in the chapter 4, Fajan's rule application, right? So higher the positive charge, smaller the size, higher the polarizing power. So polarizing power depends on the charge and size. Higher the charge, higher the polarizing power. Higher the charge, lower the size. When the positive charge increases, I am talking positive charge. Cations are polarizing anions. We are talking about the polarizing power means we are talking about cations. So higher the positive charge, smaller will be the size, higher will be the polarizing power. So which one is the answer? Anyway, you can eliminate these two choices. It will be aluminum maximum, second will be magnesium, and there is a confusion between these two. No doubt the answer is A because cesium is larger than potassium. Cesium is larger than potassium. Potassium is smaller. So a smaller cation will have a high polarizing power, and the answer is option A. Option A, aluminum 3 plus, maximum polarizing power, then Mg2 plus, then K plus, then cesium plus. Next question. There are successive ionization values are given. There are successive ionization potential values are given. 191, 578, 872 and 5962. So first value, second value, third value are comparable. First value, second value, third value are comparable, but the fourth value is very high. That indicates the fourth electron is inside the core. 3 electrons are in the valence shell and the fourth electron is inside the core, and you find the removal of fourth electron is really tough with a large jump. And the answer is option C. 3 electrons are present in the valence shell. They are asking what is the number of valence electrons possible? 3 valence electrons. So you're removing the last electron, outermost electron 191, next electron 578, next electron 872. Now the fourth electron removal, you need a huge value that indicates the fourth electron is inside the core while 3 electrons are in the valence shell. I think it is pretty clear. Next. An element with the highest IP. IP means ionization potential. No doubt helium. In the periodic table itself, the highest ionization potential values are shown by noble gases. A diagram, graphical diagram given in the NCERT. Somewhere in the top of the textbook you might have seen. Right hand page, right hand column, top. A graph is given. The peaks are occupied by noble gases. And that too, who is coming the extreme high? Helium is coming extreme high. Helium comes extreme high, and that is the answer. Neutral oxide. Neutral oxide is carbon monoxide. Carbon monoxide, nitric oxide, nitrous oxide, etc. are neutral. You are advised to prepare a table, a tabulated information for the facts of acidic oxide, basic oxide, neutral oxide, amphoteric oxide. In different chapters, you are getting information, facts on based on that. You can collectively hold on to a table and learn. Definitely 2-3 questions you will be encountering this point regarding acidic, basic, neutral, amphoteric, normal oxide, mixed oxide, etc. Next. See, this is neutral, this is amphoteric, this is acidic, this is also amphoteric. Next. An element X giving HX, an element X giving HX, and that with water giving pH greater than 7, alkaline solution, where X belong to. Why doubt? First group, because first group hydrides will be, example, sodium hydride. It is NaH. See, HX, NaH. It can be only first group, and that when treated with the water, what do you get? You get vigorous reaction. Sodium hydroxide liberating hydrogen gas. You get sodium hydroxide liberating hydrogen gas. Right? So the answer is first group. Option A. 1 mole magnesium in the vapor state absorbed 1200 kilojoule of energy. Delta HI1, delta HI2 of magnesium are given. The final composition of the mixture is, you see, 1 mole magnesium absorbing 1200 kilojoule, while the first ionization enthalpy 750, second ionization enthalpy 1450. Right? You see, suppose you are taking magnesium 1 mole converted to Mg plus, and from there it is converted to Mg2 plus. For this conversion you need 750. For this conversion you need 1450. So for total conversion you need 750 plus 1450. Etraya to 200 kilojoule. This much energy is required per mole for 1 mole conversion. Isn't it correct? 1450. Yes. 200 kilojoule is the energy required for the complete conversion of 1 mole magnesium. But that is not absorbed. Absorbed quantity is only 1200. Absorbed quantity is only 1200 kilojoule. If there is this much, you will get entire 1 mole converted. Now it is clear that 1 mole conversion will not happen completely. So what is going to happen? Let's see. Suppose I am taking 1 mole here. Initially here it is 0. Here also 0. Now 750 joule out of this 750 is consumed. You can see 1 mole converted to this, and this becomes 0, and this becomes 1 mole. And now the consumed energy is 750. This much consumed because 1 mole converted to 1 mole. Okay, fine. So how much is remaining? Out of 1200, 750 consumed. And 1 mole of this converted to this. Just imagine. So what remaining is how much? 450 remains. Now using 450, can this entire conversion take place? No. Because for the entire conversion of this, you need 1450. For 1 mole to be converted, you need 1450. We have only 450. So how much it will be converted? For 1 mole conversion, you need 1450. Here the energy available is only remaining 450. So how much conversion will take place? How much conversion will take place? Very simple. It is 450 by 1450, approximately 500 by 1500. That is approximately 1 by 3. That is some 33%. Isn't it? Some 33%. Approximately. I am talking approximately. So the conversion here to here happening is only 1/3. 1/3 conversion takes place. So out of 1 mole, only 1/3 will be converted. So here available will be Mg2 plus we are going to get will be only 1/3 mole. That is some 33% approximately. That will be Mg2 plus. Quite naturally, this will be some 67%. So this will be some 67%. This will be some 33%. And hence you can select which will be the correct answer. See what I said, figures are approximate. Suppose there is a closed figure, we have to work out further. 31 mg plus and 69 mg2 plus wrong. 69 mg plus 31 mg2 plus. That will be the correct answer. That will be the correct answer. Some 69% there will be mg plus remaining, and some 31% mg2 plus formed. Hope the calculation is clear. So the total energy absorbed is 1200, out of which 750 consumed, 1 mole converted to this, and this remaining is 0. Now this is 1 mole. So 1 mole to be entirely converted to this, you need this much. So 1 mole conversion, you need this much. What energy you have is 1200. Now this much is consumed already here, remaining 450. Using 450, how much fraction you can convert? It is 450 by 1450, close to 500 by 1500. That is 1/3 conversion taking place. That means some 33% it will be converted from Mg plus to Mg2 plus. So Mg2 plus formed is somewhat 33%. And Mg plus remaining will be somewhat 67%. That somewhat figure will take you to the answer. Right? Next. Option B, correct. Electronegativity of carbon is highest in the compound. Electronegativity of carbon is highest in the compound. I am sure all of you know electronegativity is not the property of an isolated atom. It is the property of an atom in the bonded situation. And as far as organic molecules are concerned, if you take, see, this carbon is less electronegative compared to this carbon, which is less electronegative compared to this carbon. All of you know this is sp3 hybridized carbon. The percentage S character is low. Here it is sp2 hybridized carbon. The percentage S character is increasing, and here it is sp hybridized carbon. The percentage S character is high. Here it is 50% S character. Here it is 1/3 S character. Here it is 1/4 S character. So S character here is 50%. Here it is some 33%. Here it is some 25%. That too is a relevant point based on the chapter 4 hybridization, and which is influencing the electronegativity of the concerned carbon in organic molecules. So electronegativity is not a fixed property. It depends on the nature of bonding. So keep it in mind, single bonded carbon is less electronegative than double bonded carbon, which is less electronegative than triple bonded carbon. You know, this is alkane, alkene, alkyne. This is alkane. This is alkane. Oh, this is same compound. And this is alkyne. This is ethyne. And that is the answer. In ethyne, you have CH, triple bond CH. That is ethyne. And this carbon is more electronegative. Next question. How much energy liberated when 1 gram of chlorine atoms are converted to Cl minus? Electron gain enthalpy given minus 349 kilojoule per mole. Simple. 1 mole chlorine when converted to Cl minus. 1 mole chlorine means 35.5 gram. You know the atomic mass of chlorine, 35.5 gram. 1 mole chlorine, 35.5 gram. The energy liberated is minus 349 kilojoule per mole. Therefore, 1 gram, how much? That is the question. 1 gram, how much? That is the question. So it is minus 3, isn't it 1 gram? Yes, 1 gram. Minus 349 divided by 35.5. It is approximately worked out 350 by 35. Think it. 350 by 35, close to 10. And the answer is greater than 10 or less than 10. See, the approximate answer will be 10. You see, 350, 355, 35.5, 355, 35.5. Suppose you are assuming this figure to be 355. Just imagine. Then it is 350 by 35.5. It is 10. So the approximate figure is 10. Is it less than 10 or greater than 10? Less than 10. Because in the numerator, approximation went to 345, 355. Actual figure is 349. So the actual answer will be less than 10. Slightly less than 10. Slightly less than 10. It could be option D. If you have a confusion, you can work out. Not necessarily. Okay, slightly less than 10. It is option D, 9.8. Yes, option D, 9.8. Next. You have to identify the elements X, Y, W, Z. You see, there is a reference given antimony. So this is nitrogen family. So this is nitrogen and this is phosphorus. Nitrogen, phosphorus, arsenic, antimony, bismuth. That is nitrogen family. And this is oxygen family. Oxygen, sulfur, selenium, tellurium, polonium. We don't want anybody here. And the next is halogen, fluorine, chlorine, and this is bromine. Bromine, iodine, astatine. And this is carbon family. This is carbon family. Nitrogen, the previous one, carbon family. Carbon, silicon, germanium, tin, and this member is lead. This is boron family. Boron, aluminium, and this is gallium. Gallium, indium, thallium. These are the members. So what are all we are looking for? X is gallium. X is gallium. We get our answer. X is gallium. We get our answer. Simply tracing X, you get your answer. Then what is Y? Y is lead. What is W? W is P. What is Z? Z is bromine. So checking whether you know the relative idea of the periodic table, that's all. The fragment of periodic table, whether you've been able to recollect or not. Next. A simple, beautiful question. Atomic number of element electronic configuration 5F14, 6D10, 7S2. 5F14, 6D10, 7S2. That must be the last member of a D block. 6D10, 7S2. It must be a last member of D block in the new elements. Okay? And which is the last member? Which is the last member? You can easily identify. See, D block starts from group 2 to group 12. Group 12 element, more than 100 atomic number, group 2 element. Sorry, group 12 element. It will be 112. It will be 112. 112 in group 12. 113 in group 13. 114 in group 14. 115 in group 15. 118 in group 18. Okay. You see, D10, S2. It is coming with the zinc, cadmium, mercury. It is coming with the zinc, cadmium, mercury. You see the comparison of electronic configuration. Zinc, D10S2, cadmium, mercury, and the next member. Who is that? It is, see, all these are available in group 12. That is the last member of D block. D block start from group 2, end at group 12. So that is ending elements. Ending element means group 12. Group 12, new element, more than 100. What is element? 112. I think all of you know it is copernicium. It is copernicium. Copernicium, that is the element. Known after Copernicus. Copernicium, Cn, atomic number 112. Extremely radioactive element. Copernicus, known after Copernicus. Copernicium. Next. 23. You see atomic number 11. Atomic number 11 is sodium. Sodium is in group 1. So A with 1. A with 1. So this is out. Now 35, all of you know it is bromine. Bromine with the group 17 halogens. So B with 2. B with 2, correct. Now see if you get your answer. C 58, 57. 57 is lanthanum. 58 is cerium. Lanthanum is in D block and cerium is in F block. So C4D3. C4D3. This is the correct answer. Option A. Lanthanum 57. After 57 lanthanum, 58 to 71. Cerium to lutetium. F block elements. So 58 cerium is in F block. C4. That takes you to the answer. Okay, next. (24). Which pair react with the most violent passion? Most violent passion. What doubt? Option 3, cesium and fluorine. Cesium, the most electropositive element. Fluorine, the most electronegative element. They are lying diagonally opposite. Cesium is most electropositive, fluorine is most electronegative. They react with the most violent passion. Right? Yes. For alkali metals, the reactivity increases down the group. For halogens, the reactivity decreases down the group. So halogens, the reactivity is maximum on top, fluorine, uncontrollably reactive. And alkali metals, cesium, highly reactive. Next. In transition elements, the differentiating electron occupies n-1 sublevel in preference to. In preference to. Simple to find out, right? Suppose we are taking any transition element. Say I am taking, say, iron. You take any transition element. You take any transition element. Say if you are taking iron, atomic number, say, what is atomic number of 26? 26. It is 3d6, 4s2. 3d6, 4s2. Right? And electronic configuration happens here. This is n-1d. And this is ns. This is n. And this is n-1. So n equal to 4, n-1, 3. Like that. So electronic configuration occurs here in preference to. In preference to which? That means after this 3D, which one comes? That is the point. All of you know it is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. It goes like that. Off-bow principle. So 3D is coming prior to 4p. 3D is coming prior to 4p. 3D, that is 3 plus 2, n plus L value 5. 4p, 4 plus 1, 5. Both are having same n plus L value. And the priority goes to, the lower energy is the one with the lower n value. So the energy filling occurs here. So this is filled in preference to 4p. 4p means np. 4p means np. N is equal to 4. n-1, 3. 4p means np. np. Option A. So it is being filled preference to 4p and it is being filled up after 4s. So n-1d filling occurs after ns and it is before np. Next. Twenty-sixth question. Group 13. Group 13. Formula of oxide and nitride. Group 13 means boron family. Boron, aluminum, gallium, indium, thallium. So what is the formula for oxide, aluminum, boron? What is the formula for nitride? Aluminum oxide is Al2O3. See, if you check with an example, very simple, no? Al2O3. Aluminum nitride is Aln. Aln. So this is aluminum oxide. This is aluminum nitride. This is boron oxide B2O3 and this is boron nitride Bn. Enough to get your answer. Enough to get your answer. Either option C. Because they are trivalent. Their covalency coming 3. 3 plus state. Next. Option C. Anomalous behavior of first member. See, in all representative elements, first member is anomalous. Group 1, lithium. Group 2, beryllium, boron, carbon, nitrogen, oxygen, fluorine. All of you know The first member is abnormal. First member is abnormal. Number one, tendency to show a maximum covalency of 4. Their maximum covalency is limited to 4 because they don't have a d orbital. You have learned without a d orbital, they are having only 2s and 2p. Their maximum covalency is 2s, 2p. 4 is the maximum covalency. They usually form p-pi bonds. They usually form stable p-pi bond, except halogens, that is particularly fluorine. Ability to expand covalency over 4, it is not possible. So it is option D, A and B. These two statements are correct. Answer is option D. Next. Ionic radii of C4 minus O2 minus respectively given. Most probable radius of N3 minus. See, they are isoelectronic species. C4 minus, O2 minus, N3 minus, they are all isoelectronic species. They contain 10 electrons. For isoelectronic species, what is the nature of the size? What is the nature of the size? Higher the minus charge, higher the minus charge, lower the effective nuclear charge. So the size will be greater. Okay. So the order of size will be C4 minus maximum, C4 minus maximum, then it will be N3 minus, then it will be O2 minus. So this is coming between the two. The size of N3 minus will come between that of C4 minus and O2 minus. So what will be the value? C4 minus is 2.6 and this is 1.4. So this is 2.6, this is 1.4. So what could be this value? It can't be A, it can be B, it can't be C, it can be D, right? See, it cannot be 2.6, it can be 1.7, it cannot be 1.4, it cannot be 0.95, only one answer, 1.7. We don't know, is it 1.7 or not, we don't know. It can be that choice among the list because it is coming between the two. Okay, next. Correct order of ionic radii. Correct order of ionic radii. Once again, looking at the choices, you can understand they are isoelectronic. They are isoelectronic species. For isoelectronic species, what is the order? The one with the high positive charge will have a high nuclear effective nuclear charge and their size will be lower. So higher the positive charge, lower the size. Higher the negative charge, higher the size. So what is the answer? Higher the positive charge, lower the size. So it can be either this or this. It cannot be this. You see, this is wrong. This is wrong. So the answer is option D. 3 plus, 2 plus, plus, minus 1, minus 2. So minus 2 oxygen maximum, Al3 plus minimum. That's order. Right? Next one. Correct order of ionization enthalpy among the following elements. Correct order of ionization enthalpy among the following elements. See, this you can relate with the, here the elements given are third period. Okay, you see sodium, aluminum, magnesium like that. This you can relate with the second period element. What is the order of second period element? Already we have discussed. What is the order of second period element? Lithium. Among lithium, beryllium, boron, carbon, nitrogen, oxygen, going like that, we found two abnormal cases. One is here and one is here. Right? And right, this is coming before this. So this will be the order. And here also, nitrogen less, oxygen less than nitrogen. And we have seen an order. And the reason also, what is the reason? We have seen. Now, check with the third, the next member from the corresponding family. It is sodium, it is magnesium, it is after boron, it is aluminium, after carbon, it is silicon, nitrogen, phosphorus, oxygen, sulfur. We don't have to go up to sulfur. We don't have to go up to sulfur. Only 4 is enough. Only this much is enough. We don't have to look at that side. Anyway, like the abnormality here, there will be an abnormality here. It is going to be aluminium less than magnesium. Magnesium will be slightly greater. And the reason is quite same. Quite same. In magnesium it is S2 configuration. In aluminium it is S2P1 configuration. So what will be the order? What will be the order? Sodium minimum, then aluminium, then magnesium, then silicon. That will be the order, which is similar to an order we have seen in this case. So which one is the answer? Sodium, aluminium, magnesium, silicon. Sodium, aluminium, magnesium, silicon. Option B is the correct answer. Option B is the correct answer. Yes, option B. And see, the data is also available. You see, sodium 496, then magnesium 738, aluminium 528. You see that? You see that? So it is sodium, then it is aluminium. Sodium, then it is aluminium, then magnesium, and then silicon 789. Goes like that. So that was the last question. That was the last question to discuss from the concerned chapter. So we have gone through some typical example questions from chapter 3, that is classification of elements and periodic properties. Okay, we will meet in another class, another chapter, similar questions. Okay, bye, see you.